So we're going to start just a little early because most people are going to come in late anyway. And first a question though first. I give this presentation at very different types of groups. This one was sort of all the graph explanations that were in here before are gone because you know what a graph is. But when I'm giving this presentation to like certified fraud examiners, that's all in there. How many people here have some formal training in machine learning? Uh-oh. Okay, well this is going to be C-spot run for some of you then. And this is something I had to put together for basically a 35-minute presentation. It's kind of a Frankenstein because I got bits and pieces from different places, but that's really the only way that I could do this. So for those of you who don't have exposure to data science, I have some things for you, and it helps me explain how I apply it in what I do. Okay? So that's me. This is my company. We are an investigations firm. That's what we do. We also do consulting and information governance. A lot of what I'm talking about today is investigations, but we also do consulting for information governance, which is a lot more, I guess, high-powered in the use of data science. Today is about actual investigations. We leverage all kinds of things. We use Neo, we use Elasticsearch, Solar, Less, and a whole bunch of things. Open source, APIs, Python mostly. And we sell information. I don't sell analytics. People say, oh, we're the analytics firm. No, we're the information firm. We use it behind the scenes. I know how to apply it. I use it. And you'll see kind of how that works as I go through this. I have 70 slides, so I have to kind of move quickly. But they're slides that are graphic that are meant to kind of go quickly. Okay. So this is me. I'm a licensed private investigator and attorney, so I can kind of, discuss the law. I have a Master of Science in Predictive Analytics, which I finished last year, and I've been working mostly with Python and mostly the Apache project tools. And I use those tools to help me do what I need to do. But most of all, I'm an investigator. So that's what I am. That's what all that other junk kind of facilitates. So what this talk is about, I don't know if you read the description, this is not about how many clusters you have, how quick you can make a query or a join happen in milliseconds. This is not about that. This is exploratory. So I'm going to use certain tools, things that lots of people use, and this is actually in my space, the things I'll talk about are fairly commonly used, these data science tools. I see them used all over in some of these other presentations like information extraction and things like that. So, and the other thing is, because it's exploratory, is this too loud? Okay. It can be used, as you probably know, you use the patterns, the statistics, whatever you find to help you build predictive models to be used as proactive solutions, maybe in an enterprise network. But we're going to go kind of more pedestrian today. It's a little bit more, I think, fun perhaps. So what I'm going to do is first dive into big data, just make sure we're data science and big data, and kind of make sure we're on the same page, why it's important for what I do. And then I'm going to go into fraud investigations specifically. What things do we use in data science and with electronic data to help us focus on where we need to be? And then I'm going to be talking about fraud and conspiracy, collusion, and conflict of interest. That's kind of where graphs come in to be the most useful for this type of investigation. Then I'll get into some other sort of a configuration. Again, not one I invented, one that I know is used fairly commonly. So, data science. We basically know that data science, machine learning, predictive analytics, artificial intelligence has become one of the most important competitive aspects of being competitive. Did I say that right? It's very important in being competitive to use data science, to leverage your data and use it in a very efficient way. That's especially true in legal. When I say legal, I mean fraud, compliance, and things like that. So if 90% of the data is, 90% of the place where you can get your information is electronic, data science is an obvious solution. How do you define big data? You hear the 4 V's, it's voluminous, here's veracity, like very complex, velocity, fast moving. I just say data that's out of hand. If you have conventional methods and those methods can't handle the data science is typically the answer. Data science is the solution, essentially. Big data is the rain, data science is the umbrella, is the way I like to put it. And the most important thing is it's contextual. I spend most of my time telling people what it is and how it applies to what they do. I'll get into that more a little bit later. Where I work from is in information. I don't know where that information is going to be, so I have to think about everything. Structured data, unstructured, quantitative, categorical. I have to think about everything. So I personally maintain more of a jack of all trades, and I bring in PhDs if that's what I need, depending on what I need to do to marshal my case forward. Everything that's done in electronic form has to be followed up on. Most of what the data science tools I use are for lead generation. I want to know where I need to focus. Okay? So very roughly, and some of this is a little bit wrong for some of the data scientists in the room, I know that. I'm taking a little liberty here. There's quantitative. Data science is math, right? So there's numbers. There's what I call qualitative. It's really categorical is the way I mean that. But I'll explain that in a minute. And then there's structured data and unstructured. So I have to think about the entire sort of holistic way in which data can come to me. And then, of course, unstructured data has to become structured. Okay? Qualitative, or really categorical data, you have to use numeric aspects of those things, like words, my name, Paul Starrett, right? I can't plug into an equation, but my age, 29, no one's laughing, you're not listening. My age, or my weight, 165. I know if you're listening, if you're laughing. Or like words, how far apart are words from each other in a document? Or how dense are they? So you're using numeric aspects of things that are otherwise not numbers. Make sense? Okay. So we're going to go through fraud investigations briefly, and then I'll get into what I call New Horizon. It's really sort of a new configuration that I see used very often. First thing is, I don't just use electronic data. I interview people, I interrogate. That doesn't mean hot lamps and finger pointing. It's more of a negotiation, but we do it. That's one of our most important sources of information, frankly. Surveillances, yes, we use those too. Like an anti-money laundering case. Let's say a laundromat says it's making $1,000 a day, but you put a surveillance person on there, all you see is 3 people walking in with a shirt, right? What's wrong? They're claiming they're making $1,000, but they only have 3 people with shirts. What's that, a few $100s? Money laundering. They're trying to make it look like money's coming into the entity, and it's not. So is that important? Absolutely. Then there's the financial records, the email, and yes, graphs, okay? And we use them iteratively. I don't just go to the graph and push a button and, oh, isn't that neat? I go in and out of it. I might merge new data into the graph. So it's very kind of iterative and different permutations. This is the most important slide in the whole deck, I think, for my purposes. There's a sequential process. When I talk to a client, I first get to know the law, the policy. Is it compliance? Is it a fraud investigation? What are their priorities? What's their budget? Do they hate that I'm there? Do they want me there? I don't know. Based on that, I then go and say, well, what data do I need, right? I don't need everything. In fact, I only want only as much as I need. And it's only at that time that I can say that I'm going to use data science, okay? And I can tell you that 4 out of 5 people I meet in the legal profession like to go the other way. Show me how graph database fixes that problem over there. And I know that conversation is not going to go anywhere. And I know I'm happy that most of you, when I talk here, when I come to a technical audience, they go, well, of course, which is very refreshing, frankly. And we keep things simple. We always if we could use, generalized linear models or ensemble techniques, just use regression. Just use a simple regression because people understand it. When I talk to a CFO or whatever, I can explain it to them, which I'm going to do today. 2 ways we determine fraud is, by the way, if I keep looking over there, it's because of the clock. Anomaly detection. Fraud is usually identified in one of 2 ways. What's not normal? And I'll show you examples. But anomaly detection is one way. When you don't know anything else, you use anomaly detection. What's weird? What doesn't fit? The other thing is predictive analytics, where, again, many of you will probably identify with this. Known fraud samples and other non-fraud samples, and use the patterns on those too to help you determine what that's out in the real world may or may not be a fraudulent event or scenario, right? So those are the 2 patterns, or the 2 ways that we generally work. Who knows what standard deviation is? Okay, good. Most of you don't. Basically, it's the average. This is all simple. I'm trying to make it like really simple. That's part of my purpose here. Standard deviation is the average distance from the average. So if we had a room full of people, half of you were 30 years old, half of you were 50, what's the average? 40. What's the average distance? 10, right? So this is my way of kind of trying to show you what that is and how it works. But these are little distances away from the mean or the average. So which has a larger standard deviation? This, right? Because the distances are farther away. That red line is my attempt to draw a standard deviation line. And what stands out? D6, D7, a little bit of D2. So an example here, this is one numeric variable. If we're doing anomaly detection, we're trying to say what's not normal. Anything inside the standard deviation is normal. A lot of times we use 2 standard deviations as a thing. But like on a loan amount, what if there's a bunch of loans that are too small? Someone doesn't want $1 million loan, they take out $10,000, $100,000 loans. They're trying to go under the radar. That's anomalous. Make sense? Earth audience? Okay, now what if 2 numeric variables? This has come out very well. So here, salesperson, calls per week, millions of sales per month. It's correlation, right? Linear relationship. And we can also use this line here to predict. So if I say, how many calls do I have to make $5.5 million? I have to make 2.5 calls. That's an average, so you're not going to get half a phone call, of course. But so that's how the correlation establishes the norm, and the predictive analytics, the regression, helps establish finding anomalous data out in the real world. Does that make sense? Okay, so down here, who's this guy here? That's an anomaly. That's an outlier. How is it this guy's making $13 million a month with 1 phone call? Maybe he's a superstar. Maybe he's taking kickbacks. You know, he's not making any calls. He's getting money from his clients. Does that make sense? Yes? Okay. Does it? I mean, how many thumbs up for people it makes sense? How many say it doesn't? Okay, thanks. Okay, classification. Again, it looks like this didn't come out quite right, but it's talking about categorical variables. And you'll notice here, when I show this to lawyers and so on, they love it. They don't like technology, they love cats and dogs. So that's why I'm talking about cats and dogs here. On the right is the classes, dogs and cats, and you'll see these records have different variable values like hair length, the number of ears, and whether it has a tail or not, which is useless. That's there for a reason. Those columns are useless in this model, so those will get removed. Cats don't have the muscles in the eyes. They don't have that. So that variable alone would probably be enough for me to predict in this model. But these are the classes. So what happens is the predictive model, it learns this. Then you say, all right, Mr. Smart Model, now I'm taking away the information. You try and predict what happened. And then you'll get an accuracy. And some things will be wrong here. And you get things false positives, false negatives, rock curves, and all that kind of stuff. Can't get into that today, but this is basically how machine learning works. You have classes over here, dog or cat. We could add a third class. Maybe you're looking for giraffes or what have you, right? Could be relevant to a lawsuit or not. Could be fraudulent or not. So maybe this class would be fraud, and these would be patterns showing fraud. The next one down might be a non-fraud pattern. That would then be added to help you separate the 2 types. Okay? Make sense? Okay. Clustering. This helps us I'll show an example of this, if I can finish in time, of how you group words in documents. These like k-means clustering or hierarchical clustering. Go into those documents and bring me back all the different concepts you find. And it groups things into patterns. So you can say, this is grandma's recipe for apple pie. I don't need it. Oh, this is an R&D project where someone might have taken some trade secret. So I can figure out what I want and where to focus. It helps me kind of explore the data. Okay, now I'm going to get into fraud. Fraud elements are common sense, but it's a false representation of material fact. It has to be about a fact, and it has to be material. It has to be something important. And the defendant has to know it's not true. They have to have an intent to deceive. And the victim has to rely. If the victim's going, he's joking me, it's not fraud. They have to actually rely on it. And then the victim has to suffer loss, lose money, do something they wouldn't otherwise do, for example. There's criminal elements, and there's civil. You can sue for fraud civilly. It's called intentional misrepresentation. Conspiracy, an agreement between two or more persons to commit one crime, and that person's intending to help commit that crime, okay? And in certain states, because state law is usually, criminal law is usually a state, there's civil conspiracy too. But this is a state law thing. Some states you don't have to do an overt act, like go buy a gun. Others, you just agree, you're guilty, okay? And it has to be a conspiracy to commit some crime. You can't say, he's guilty of conspiracy. Guilty of conspiracy to commit fraud. Guilty of conspiracy to commit murder, okay? Graphs are helpful with this, which is why it's up here. Conflict of interest, another big area where graphs are useful. Two parties who have interests that are incompatible. And then the other one is someone who's going to take a personal benefit in their official capacity. And we'll get into that a little bit as we move through this here. Okay, now, this is kind of the holy grail for me, is I want to be able to take structured data and unstructured data and bring it together into a graph. And again, this is for an investigation. I'm interviewing people, I'm videotaping perhaps, I'm doing all the gumshoe stuff too. But we're also doing the high-tech things as well, okay? So that's the idea. And this is the basic approach that is being far more often now being used as a investigative technique. And you see these things in the bigger enterprise, threat detection systems, the same things that work, but only in fire hose capacity. Original files, we're working with text here. We're extracting the text out of the files, putting it into a text repository like MongoDB or Cassandra, right? And we're retaining all that original metadata, the file name, the date, what have you. That's all being kept here in the text file repository. We're also taking that same data and we're creating a search engine from it, what I call information retrieval, which is it's an umbrella term, but it's search engineering, basically. Then you'll see how this kind of unfolds as we go. So I really need to keep with the pace here. So here's just a deeper dive. You'll notice that first thing is probably a Microsoft Office document. The second one is like a inventory record or some financial record. The next one's an email, right? This is a website. There's all this stuff that's going to go into the text repository and also ultimately into the search engine. So information retrieval. So I actually wrote this book on about 2012 on digital signatures, so I have copyright to that. But think about, if you had to go through a book to look for someone's name, right? Would you start on page 1 and skim each line? No, you go to the index in the back, right? So it would take you forever to go through the whole damn book, right? I mean, this is what an index is. I'm sure you all know what that is, but the idea is that you just go to the back of the book, look up the term, and it tells you exactly where that is, right? I mean, I think probably most of you know about how search engines are made. There are things like stop words, like the word the and to, and useless. You don't want to search for them, and they're going to make your index enormous. So you remove them. Tokenization, breaking things down into words or word combinations, so that when you search, you're getting back, you're searching on exact targets. Case conversion, to turn everything to lowercase, so when you search and you wind up doing my name capital P, Paul, you'll get it back in the search. Stemming and lemmatization, where you're basically reducing things from like running and ran and run, reduced to run. So if you search for one version of a word, all versions of that word come back in your search. And you have to make those same transitions in query expansion, I guess they call it, in your transformations. This is what it looks like when you get done. This is what's called a, am I going too fast? Okay, you probably know this anyway. But so this is what it looks, it's called a sparse matrix. Why? Because when you add a document, you have to add a column for every word that's in the document. And it becomes this big, ugly, 4,000 column long, 10,000 row deep thing. So what they do is create what's called an inverted index. Take this ugly thing and turn it into this. Document 1, you notice, has the word dog and simple in it. So dog has simple. The word dog is in document 1 and document 5. So this is a far simpler, more straightforward way of representing that same information, right? Then there's a thing, how many people have heard of TF-IDF? Okay. You heard of BM25? Okay, yeah. I think Elastic's using that now, I'm not sure. Okay, yeah. Whoosh is too. If you heard of Python Whoosh, it's a cool search engine. Try it, it's all Python. Term frequency, all this is doing, it's an unsupervised machine learning approach to finding important words in a document collection. The theory is that if a document appears many times, a word appears many times in a document, it's important. If it appears many times across the document population, document collection, it's not important. So word's going to get kind of balanced between those two things, and it will ultimately get a score. And I have grossly dumbed this down in my next slide here, but it's used for search relevance ranking and for keyword identification, which I'll be going into a little bit later. So what you do is you add the TDF-IDF score to the inverted index. So here the word apple is in document 3, but in document 3, apple has a TDF-IDF score of 4, whereas the one in document 6 has 5, because it probably appears more often. So when you run a search for the word apple, which document's coming up first? This one, because it has a higher TF-IDF score. I'm surprised I can even say that today. Does that make sense? Okay. Okay, now, so what we've done here at a high level is we have gone in and we have searched for our documents. We've created the search engine and we run a search and we get a result set. We're saying of all the documents that are in the search engine, I want to look at these 100 documents. So we get down now to the second stage where we're going to go into the text file repository and we're going to remove structured data from that side if we want it. Depends on the case. And then from the free text, the unstructured stuff, it's going to go into natural language processing so we can take that and leverage it. And note that when we take data out of the natural language processing, out of the free form text, we're going to wind up with what could be name value pairs, like a location. This technology goes in, oop, that's a location, plucks it out, it says location, like in a column, and it structures it for you. And I'll show you how that works in a minute. But that's the idea, because when I'm doing investigation and I've got hundreds of thousands of documents, I want to get right down to the nitty-gritty, okay? So here's the way it works roughly as you're going through, let's see, this. You're taking an original file, and you may choose to take the structured data. Depends on your case. Is there a part name you're worried about someone stealing? I don't know. Are there dates that are important to time series analysis? I don't know. But it's structured, so you've got the benefit of taking, here's the to address, the email, Paul Starrett. It's already set up for you. However, these things are not. They're unstructured. So that's what we're going to do now in our natural language processing, which is called information extraction. And all that's really doing is taking unstructured and we're structuring it. The first thing is called parts of speech tagging. Has anyone heard of that term before? Okay. All it's doing is it first takes a sentence, tokenizes it, applies parts of speech tag to it, and then it identifies an entity for it. And so here's the way that works. We saw the brown cats, here's dogs and cats again. What it's done is it's taken the sentence and it's broken it down, it's tokenized it into individual words, and is now applying what is it? Is it a verb? Is it a pronoun? Maybe it's a noun phrase. So it's doing this, it's looking for patterns. Now, I didn't invent this, it's just how it works. But what happens then is, in machine learning, what they've done is they've taken thousands and thousands of documents where people have highlighted a term saying, this is a person, this is a location, this is a dollar amount. And so what happens then is it's able to look at the pattern. Noun, noun, noun is 90% of the time going to be a person. So when it goes through the document that doesn't have the tag data, it's going to say, oh, aha, 3 nouns, that's got to be a person. And it's about 90% accurate. So if you see a Donald J. Trump, it's going to suck it out and hand it to you and say that's a person. That make sense? Okay, so that's how it works. And when I'm doing this because when I talk to people who don't understand this, they go, hey, that's kind of cool. When they know how it works, it's like, it's not a magic box anymore. So there's different types. There's organizations. This is what's available in Python, in NLTK, I think it is. And it will give you money. So it will go into an email, find a dollar value, pluck it out and say, here's a dollar amount for you. And it'll call it money, and you can put it in a spreadsheet. So it's pulling it out and letting you know who's in there, what's in there, all the important who, what, when, where, why. And it's doing it automatically. It takes, well, I'll show you an example. It takes my computer like seconds to do it. Key phrase extraction, this is really nothing more than TDF, IDF. There's other versions of doing this. But what you're looking for is lingo. So if there's a group that's using a certain type of vocabulary, you want to know that. It gives that to you right away. Or maybe there's some little secret words, code words that these people are using, like Raptor. Remember Enron? It will find those, suck them out, and hand them to you. There's many things you can get. You can get categories, concepts, emotion. What if you wanted to have a machine learning program go in and find all of the emails that suggested someone was disgruntled? Maybe they're a threat, right? Or maybe they're about to steal, who knows? But you can use these tools to go and find all kinds of neat stuff. Sentiment analysis, you've probably heard of that before. I don't have time to get into all that. Now, we're at the point of where's the magic. Again, this is what we're doing. We're taking the structured data if we want it. For example, a node might contain my name, but it might contain my age. It might contain my income or my position. So if I'm doing an investigation, I can put data into the graph that's useful to my investigation. And on the right side, I'm going into all of my free-form text, getting all this neat stuff and getting it right up front. And I'll show you in a real-world example. A couple examples, voter fraud. A lot of voters at the same address. That's a problem, right? What about conspiracy? You're finding people that are linked, that you didn't know they were linked until you dumped them into a graph. So you have these financial records or email or phone records that kind of help you link. And these are common. Phone records will help bring people together. Email addresses. So now you know, oh, I didn't know that person knew that person. Wow. There's more. You learn more as you go through it. I won't go into conflict of interest. That's a little bit like, we don't have time. But somebody who's buying, assets, they're oftentimes when you're doing due diligence or a merger and acquisition, you want to know who's in bed with someone else. If I'm on a board of some company and I want to buy a corporate asset, I go through a trust. You won't know it because my name's not on the trust. But I'm taking advantage of the corporation, and I'm not supposed to do that. There's also patterns in transactional data. Again, a graph, directed graph, where you have start here, start here, start here. And what it will do is it will look for common patterns to tell you what's not normal. So it says, if you're looking at this kind of transaction, these are the things that typically happen. Market basket analysis is one such thing. Shipping fraud. I had a case, I was involved in a case where they were proving that trucks would follow a certain route, would take them a certain amount of time, and certain gas stations they would stop at. Well, one guy was going way off over here and back over again. What was he doing? He was unloading stolen stuff. Well, the graph, it stood right out. It was anomalous. And it's all kinds of stuff. And you can use geospatial things in all kinds of data science-y things that it's really a kidney candy store. This is association rules. I mean, really, you're taking this thing on the left and you're converting it to what are the common patterns? How do people sequence through a site? And it's just helping you find those patterns and telling you what's normal or not. So now I'm going to get into what is my example. I'm actually not there quite yet. But look at this pattern. This is actual data that I have gotten from Bureau van Dijk, is this company. A buddy of mine works there. And then this is Polynode. Polynode's another lighter weight tool. Doesn't compete with Neo4j, so don't worry about that. But it's a great tool. This is what it is. And do you see anything that stands out that looks weird? Give you a little hint. That. So this is an entity, a Trump entity, and these are advisors. So the thing here is none of these advisors are advising other Trump organizations. So you're not worried about this because there's no crossover. There's no conflict of interest, right? So this is okay. These are probably all right. This is the problem right here. There's one advisor advising multiple. Don't worry about exactly what's there. That happens to be Price Waterhouse, North America. I'm sure it's totally legitimate, but this is real data. That would stand out to me if I was doing a conflict of interest case. It just pops out right away. There's some examples. I don't want to get into it. Panama Papers. I'm sure you all have heard of that. It was Neo4j and Python. 900,000 nodes and 1.1 million edges. Huge. Citizen.org, it's a guy I know who uses nonprofit tax forms for you to do investigations. He uses Elastic, the Elk stack, and he uses Neo4j. I'm not going to go into this, but you can do standard deviation, in degree and out degree shortest path. Was anyone in the data science training yesterday? Okay. Yeah, I mean, you got into that a little bit, and the presentation by Tim Ward just last session got into some of this. I don't have time to go into this, but I will point out that the Bayes and Markov networks are kind of like graph on. I'm an associate kind of looking into this for threat detection because it's kind of graph on steroids. But I don't want to get into it. It's just there's just too much there. These will be available, by the way, in a few weeks. So if you want to look into it. But all of these sort of data science-y large things can be used all over the place. The guy Tim Ward's talking about random forests, ensemble methods, regression. You can do almost anything with a graph that you can do with other types of data. Okay, real-world example. Have you ever heard of the Trump BuzzFeed graph? Anyone here heard of it? Yeah, Neo actually has their own version of this. You can actually download it and build it yourself. And I did this in Python. It didn't take very long. Use networkx, build a graph file, if you know what that means. Okay. So here's what the file looks like, the spreadsheet. Person A, person B, and the connection. So you'll notice that Andrew Bremberg and Mike Ferguson, Bremberg is a lifelong, I don't know, whatever it says, I didn't have room for it, right? And Andrew Bremberg is Scott Walker's policy director, okay? There's a source here, this is important. This was established by this website. So that information came from this website. And that's where the magic's going to come in here in a second. So this is what it looks like, just for the sake of, when you probably know this, but visualization is important. This looks like that, okay? I know you're graph people, so you probably know this, but this is really important for people like me to be able to, I could probably eyeball the spreadsheet, but there's a lot of value here. This just pops right out. Okay. Here's the right side. There's the connection and there's the source I mentioned. Here's what I did. I wrote a Python script, and believe me, this is go-kart. Don't like, oh, well, I'm going to do that too. No. This is like for demo purposes. I wrote a script that went to that website, copied the data down, Scrapey. Anyone know about Scrapey? The web? Okay. Copied it down, removed all the HTML tags, and I have this text file right here. So on my computer, the text of that website is right here, okay? Then what I do is I go into this file and I extract all the keywords. And we said TF-IDF, that's this keyword file. I created a KWP file on my own. I feel real important now. But that's where all the keywords from that are. Then I extracted all the named entities, the people, the organizations, the dollar amounts, whatever. That's in this file right here. Then what I do is I copy the keyword file into a property key in the graph. I also do the same thing with the named entities. So you'll see here, this is just copied right out of Neo4j's browser. There's the keywords. This is the node ID, which I added for evidence purposes, just again for our demo. Okay, and this is not a very interesting example. These are named entities, literally just plopped right in here in a comma delimited, or limited list. So what I have now is Kushner. It's what he looks like, and I have the name of the person. The keywords are one edge property, and the names, the entities are another. So what I'm doing, the purpose of this is, I started with just a cell and a spreadsheet of information on their connection. What I've done is, literally in a matter of seconds, after writing a script, spending an afternoon writing a script, I have been able to pull all that text down, pull all the keywords out for the lingo and the other whatever's going on, and the named entities that I didn't know about before. Okay? Does that make sense? Okay. There it is. Person A, person B, and there's the keywords, named entities, information extraction. The type is the actual connection. And that's what the graph looks like. This is what one looks like. There's Paul Manafort. There's probably a few chuckles in the room, right, because of him and all his whatever's going on there. And this is an actual example, one of the better ones. This is Andrew Bremer. This is Scott Walker. This is what Andrew does for Scott. I couldn't show all of the keywords because it wouldn't fit. You wouldn't read it. The better keywords are at the top off the chart. Doesn't matter. But those are all the keywords. I mean, this just took seconds. And these are all of the named entities. Now, normally I might add a key value pair, right? Say, person, Virgil Dickinson, organization, PR Week, so that if I was searching for people in my structured data, I could also identify them here in my unstructured data. So that's how that works. God, we're doing great on time. So here's the clustering I mentioned earlier. I pointed the clustering algorithm in Python at all of the keyword files that I have for the graph. And it came up with, I asked for 8 clusters, and I think 17 terms. And that's what it gives me back. Most of them are kind of nonsense. Like 6, at least you know there's some, I'm guessing that's Spanish or Portuguese or something. I don't know. I'm not an I'm not a language expert. But look at this one here. Manafort, Mr. Yanukovych, Ukraine, Russian. It stands out, doesn't it? So it gives me lots of neat, cool stuff. So what I might do is start searching for these terms in my search engine. It's just a database. You know, it doesn't necessarily mean you're going to find some smoking gun or a pattern. It's just a place to learn. And you know, it helps you really identify exactly where you need to go, the people you're looking for, and so forth. And if I do named entities, and I say, all right, look, there's this weird connection between Donald Trump and Paul Manafort, I can always take that term and go back into the search engine and run those terms again and go right back through the process. Okay, that makes sense? It's iterative. And again, you can run any query you want, you know, in degree, out degree, closeness, betweenness, shortest path, and get new visualizations and kind of draw down and look at new relationships. So everything's on the table with regard to investigation. There is no limit. So just to let you know, it's plug and play. You don't have to do what I did. I felt that was sort of one way of demoing, because there are very few data sets that you can use. So Trump was one of the few. The unrun emails are tired. You know, I mean, so I picked this. This is what I did to it. You don't have to do that. Maybe you copy the entire text file that you downloaded into the edge. But I don't want that. I want 3 pages of junk. I want just the good stuff. Okay? Another thing, this is something that, by the way, I want to thank the NEO team, Ryan Boyd, Amy Hodler, if I got that name right. They're in here, I don't know. But they were wonderful. This is one thing they gave me. This is sort of like, if we do an investigation and we establish certain patterns, we can use those in a predictive model. We can base it on that. And this is sort of this is something that's on one of their webinars, but it's like a system with a data lake and data scientists and finding patterns, and anyway. So it's sort of a, you know, I do work in this area, by the way. Generally, I'm more in this type of a thing than doing Trump analysis. But that's it. Questions? Nope.